Okay, so we already know that networks are just ways of representing information with vertices and edges. Now we're going to look at converting those networks to matrices. So below we have a network, and to its right is this corresponding 4x4 adjacency matrix. So this is the adjacency matrix. And it's 4x4, which is rows by columns. There's 4 rows, 4 columns. For the network, find the degree of A. So the degree of A is the number of edges connecting to it, so 1, 2, 3, 4. Okay, the degree of B is 1, 2. The degree of C is 1, 2, and we count loops as 2, so this is 4 for degree. Okay, the reason I'm doing this is because we'll see it's different for the adjacency matrix. Which one haven't I done? I've got A, B, C, I need to do D there. So D has degree 2. Alright, so what do we note about the adjacency matrix? Well, A and A are not connected to themselves. A and B is connected by one edge. A and C is connected by one edge. A and D is connected by 2 edges. You might also see that D and A is connected by two edges. Alright, so there's also some sort of symmetry here. So if D and B is 0, D and B is 0. So we're going to read through this. It says, the 0 in row A, column A, indicates that no degree connects vertex A to vertex A. So there's no edge that connects A to A. And you can do that for all of them. The 1 in row B, column A, indicates that one edge connects vertex A to vertex B. So that one there says there's that one connection there. Now the one that's different is C to C. So in the past we've said that C counts as a degree 2. In this one, the adjacency matrix, it's only one connection. Alright, the 1 in row C column indicates that one edge connects vertex C to vertex C, which is a loop. So in adjacency matrices, we're looking at the number of edges, not the degree. Alright. We now have planar graphs and complete graphs. So planar graphs are information or networks that have no edges crossing, but this is a little bit this definition is not as good as it could be. More accurately, the graph can be drawn in such a way that no edges cross. So if you have a thing here, like down here, you see the edges are crossing. This is actually a planar graph because you can redraw it so that no edges cross. We'll do that in a moment. So graph A is planar here, you have no edges crossing. Graph B is non-planar, alright, because if you try and move the edges around, you can't do it such that no edge doesn't have a cross, so it doesn't cross another edge. So here is an example. Redraw the graph shown in a planar form. So at the moment it's not in a planar form because it has edges crossing, but if I just move one of these edges that is crossing, so if I move this one, can I move that in a way such that no edges cross? Yes, you can. Let's do A, D, C, and I'm moving that one so that A connects to C but does not cross D, B. So I could go all the way around like that. That still represents the same information. You could also do it in a different way. It could have been A, D, and we'll focus on doing this one. So I'm going to connect C, and then I need D to connect to B without anything crossing. So I could go like that. Let's just check that everything's right. So A still has degree 2, D still has degree 2, B still has degree 2, C still has degree 2. Okay, so this one here looks like I've done something wrong. So C needs to connect to B, so I need another edge here. A degree 2, D degree 2, C degree 2, B degree 2, and they all connect correctly. B goes to C, B goes to C, C goes to A, C goes to A, so it looks like it's right. Okay, we also have a formula for what are called complete graphs. And complete graphs are ones with all vertices which directly connect to all other vertices. So what does that mean? It means that here's a vertex. That vertex connects to all the other ones. So it connects to that one, connects to that one, connects to that one, and it connects to that one. And that happens for every single vertex in the graph. So that one connects to that one, connects to that one, connects to that one, connects to that one. So if it does it for all of them, it's called a complete graph. And then if it's a complete graph, we have this formula that works. So the number of edges in the graph is the number of vertices times 1 less than the number of vertices divided by 2. So let's just check that, right? How many vertices here? 1, 2, 3, 4, 5. So I'm going to say that the number of edges is 5 times 5 minus 1 is 4 over 2. So 5 times 4 is 20 divided by 2 is 10. So my answer is saying that the number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that works. Okay, next one. So now we have more definitions, regions and faces in planar graphs. So at the moment this is a planar graph because no edges are crossing. You always need to consider the regions inside, and then you add this extra infinite region outside. So you can see here there's 1, 2, 3, 4, 5, 6 regions inside, and we classify the one on the outside as a face as well. So how many regions with faces in this planar graph? There are 7. Once we know regions and faces, then we can work with Euler's formula. Okay, so Euler's formula is a formula used to help us determine the number of faces, edges, or vertices in a planar graph, and it's given by this. Now this can be used with solve on your calculator. You could, if you had vertices you're trying to find, or edges you're trying to find, if you had the number of vertices and you wanted to find the number of edges, okay, you just plug in the number here, plug in the number here, and solve for E. So let's look at it in practice. A connected planar graph has 6 vertices and 9 edges. How many faces does the graph have? Okay, so it goes V is 6, E is 9 is E, there are 9 edges. We're trying to find the number of faces. So we can go to these formulas at the top here, or you can just use solve in the calculator. If you're trying to find faces, we could do this. The faces is the edges minus the vertices plus 2. So the edges is 6 minus the vertices, edges is 9, sorry. 9 minus 6 plus 2. So 9 minus 6 is 3 plus 2 is 5. So there are 5 faces. And this graph is 1 such that it fits the information that we were given, right? There are 6 vertices, 1, 2, 3, 4, 5, 6. There are 9 edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we count the regions or faces, 1, 2, 3, 4, and the outside one is classified as 5. So it all works. You could have also used solve in the calculator like the following. Solve 6 equals 9 minus f plus 2, comma f. Okay, more definitions. So a walk is a sequence of edges which can have a repeated edge. So here, A goes to C, C goes to A to C, C to A, then goes to D, A to D, and then goes to G, D to G. So that's classified as a walk. It's a sequence of edges linking successive vertices. Okay, a trail is a walk with no repeated edges. So you see here, if you start at B, go to E, go to F, go to C, go to B, go to A, then that does not repeat any edge. A path is a walk with no repeated edges and no repeated vertices. So in this case, you start at A, go to D, go to C, go to F, go to E, go to B. You haven't repeated any vertices and you haven't repeated any edges. A circuit is a trail that starts and ends at the same vertex with no repeated edges. So this one here, we're starting at B, we're going B to A to C to F to G to D to C to B. Okay, you see that you go all across there and you haven't repeated any edge, and what's also happened is you've ended up at the same vertex that you started at. Start and end is the same for a circuit. Okay, and a cycle is a path with no repeated edges, no repeated vertices, and starts and ends at the same vertex. So in this case, in a circuit, right, can you see that we did repeat a vertex? We repeated C. We went through C twice. Well, in a cycle, you don't repeat a vertex. So in this one, you're starting and ending at F. You can go E, B, C, F. You get back to F, and that's the only repeated vertex. It's a closed path. Okay, it's closed because it goes back to the same point where it started. Sorry. Okay, so here's the summary, and let's do an example. A walk, you can have a repeated edge and you can have repeated vertices. A trail, you can't have a repeated edge, you can have repeated vertices. A path, you can't have repeated edges, you can't have repeated vertices. A closed walk, repeated edges are permitted, yes. Repeated vertices permitted, yes. And they finish, no, that's okay. A circuit is a closed trail. Repeated edges permitted, no. Repeated vertices permitted, yes, but it starts and ends at the same at the same point. That's why it's closed. And a cycle is no repeated edges and no repeated vertices apart from the end. Okay, so here's the example. Is the following a walk, trail, circuit, or cycle? The first thing we notice is, well, G1 to G1, it starts and finishes at the same point. So it looks like it's going to be a circuit or a cycle. And now, what are we doing? We're going from G to F. So B to W to T to G to B to G. Okay, so what's happened? Have we repeated any vertices or edges? We definitely repeated that vertex. So repeated vertices allowed? Yes. Repeated edges? Have I repeated any of the edges? No. So it looks like it's classified as a circuit. Okay. So this one here is called a circuit. And that's it. Hope it helps.